I'm happy to be here. I'm going to talk about the high throughput toolkit and the open materials database in an elevator pitch format. So what is the high throughput toolkit? It's a toolkit for preparing and running calculations. So this is the tool that we use in quite a bit of our own projects, but it's also an open source Python software available on the internet. You can pip install it and so on. It has routines then for, as I said, preparing and running calculations, analyzing results, and store them in global and/or personalized databases. And the primary focus when this was put together was really automation. Automate as much as possible. Of course, you all know that this is necessary for working with large data sets, but we also know that it's very convenient when you're working with smaller projects that everything is automated. It's a Python library plus bash scripts for the interaction with supercomputers. And I mean, we have seen a bunch of similar tools being talked about today. There is an overlap with PyMatGen, Fireworks, Custodian, AIDA, Airflow, QMP, IC, and so on. I'm going to say a little bit more about what's special about httk in a minute, but then we have this open materials database, and again, compared to many of the other databases being presented here, Nomad in particular, I would say, this is quite small, but also in my view, this is one of the true strengths of Optimade to really be able to provide a unified interface to all these small databases that are being maintained by groups or smaller cluster of groups. And so that's what I'm hoping is going to happen here. But yeah, so the open materials database, we have had online since 2013, a web-facing database with structural and electronic structured data. There is a very simplified search interface at this point, which uses just text, but of course this is going to be optimized using Optimade in the near future, I hope. Yeah, so this high throughput toolkit, how is that different? So I just pointed some design choices to motivate why we're still using this. So it has a very integrated object relational mapper. So you can just inherit an object in this Python framework, and it builds the SQL database for you automatically, which you can store, search, retrieve, analyze with rather simple Python commands. So it's very easy to work with in that respect, and still getting SQL optimized performance out. It works with exact rational numerics. So when you're comparing cells and crystals and so on, at least with the, sort of the default settings of how things work, there is a definite answer if things are the same or not. There is an exact rational number workflow when you read in data and you produce out data. All throughout the high throughput toolkit, things can be preserved as exact rational numerics rather than floating point numbers. It has very simple dependencies. Of course, if you use more advanced libraries, you do, but the basic operation of this is it doesn't even use NumPy or SciPy. It's less important today, but it was important back when this was first designed. And you can run daemon-less scripted runs. So you queue up job managers at the cluster, and you send jobs over to be run. But it's that part of the infrastructure is very simple, so it's easy to start with a new supercomputer that way. So yes, the topic of the workshop is Optimade implementations. So we have version 0.95 implemented both inside the httk and as a freestanding server, which we probably should talk a little bit about that, because a few years ago, I don't remember exactly when, I put this under the main Optimade umbrella. But now that the Optimade Python tools have really progressed, I think I should remove that, but we're going to keep it as a httk thing. But anyway, so we have 0.95. We are working on version 1.0 release candidate 1 with good progress. I really hope that we'll get to a beta state this week, actually. This version 1.0 is then now intended to be the transport format between our database, where we store our data, and this front end in terms of web pages. So we can provide search like many others here have shown also into our database with the Optimade filters and so on. And also the idea is to really be able to work with open materials database data alongside your own data using httk. Or not just the open materials database, but anything you can pull with Optimade. Yeah, I'm also going to mention this. So since Vianney is here, the PhD student working with this, and I'm collaborating with Patrick Lambrix as well, we have started to look into the creating an ontology for materials design. Vianney is really leading this. Where the idea has been to really look into how many of the concepts are defined in Optimade and try to be inspired by that in making formal ontology definitions. Because at least in my view, Optimade represents a lot of work on finding a consensus between database efforts. So I think this is a good place to start with trying to design an ontology. That hopefully could get some traction. So we have just started, come as far as we are starting to look to coordinate with EMMO and other efforts in this space. And just so I'm finally showing some code, I have to do that. So just sort of how things in the prototype state right now is intended to work. So httk is a Python library. So in terms of clients and service and so on that we have talked about, this really happens in Python in HTK. So I mean, this is the idea that you could just take your HTK database here implemented as an SQLite database, where a backend where you can store your HTK objects, and then you can simply call the HTK Optimade serve to serve that as a Optimade endpoint. And also similarly on the client side, you could write a very simple Python program that sets up an Optimade endpoint or connects you to an Optimade endpoint, and then you can formulate an Optimade query to that, and then you directly have these structures and whatnot as HTK objects. So that is what I have to say about HTK and the Open Materials Database and Optimade. So thank you.